Hello again and welcome to our next video all about the equations which govern the Doppler effect. As you know, we're calling this series Essential Skills for Physical Science to prepare you for paper one, the physics paper, but also for living in the 21st century. I'm Dr. Derek Fish, Director of Unizulu Science Centre at the University of Zululand. This is part 6.6. We're still looking at specific examples of equations, in this case the Doppler effect, and you'll find this on pages 55 to 57 in your booklets. Hello again, and if we're going to learn about the Doppler effect and sound, we need to understand something about the difference between volume and pitch. Now, volume is whether something is loud or soft. Like this, if I play softly, that's a soft volume. And if I play loudly, I think you understand that concept just fine. What about pitch? Pitch is whether something is high or low. So I can play Happy Birthday very low, or I can raise the pitch, or raise it even further. So as you move up the piano, the pitch increases and the frequency increases. The note in the middle of the piano, that we call middle C, has a frequency of 262 hertz. That tells you the string inside the piano vibrates 262 times every second. As we go up, we double that. An octave, what we call 8 notes, we double that and it becomes 524 hertz. Again, we double that, it becomes 1048 hertz and 2096 hertz. So as the frequency increases, the pitch increases. And if we go down the piano, we could get to the lowest note, which has a frequency of just 40 hertz. As we always do, before we go to page 55, let's go to the start of your book, the contents page on page 3, and just see where this fits in. Remember, we're looking at 4 skills: graphs, free body diagrams, equations, and multiple choice and ratio questions. We're now looking at equations, and in particular, we're focusing on the equations which govern the Doppler effect. This is always question 6 in your matric paper. Once again, a comment from the examiners: learners still cannot work with scientific equations or formulae. And the Doppler equation is quite complicated because it can exist in 4 different variations, depending on the pluses and minuses. But don't worry, I'm going to explain everything very carefully. Just stay with me. Looking at the curriculum, which you'll find on page 4, of course, this falls under wave, sound, and light. The Doppler effect itself comes up only in grade 12, but in order to understand it, it is a wave effect. It's very important that you remember your grade 10 work, transverse waves, longitudinal waves, and terms like wavelength, frequency, amplitude, period, wave speed, and so on. These are all very important, including the qualities of sound, pitch, loudness, quality, and ultrasound, and so on. I hope that my performance on the piano helped you to understand these a little bit better. And that was an experiment on the demonstration of sound. So on page 5, with the breakdown of the paper, remember this graph shows the average number of marks per question. The 10 questions are always the same, not the same question, but the same subject area. Question 6 is on the Doppler effect, and on average over the last 3 years, it has been 12 marks. So it's one of the shorter questions, but still important to get those marks. Here's a look at the Doppler effect questions over the last 3 years, 2018, 2019, 2020. 2018 was a straight calculation from the equation, and we will be going through all of these very carefully. 2019 was a very different question with a sine wave graph, and it threw everybody out. So we'll look at this one especially carefully. And 2020, again, a graph, but a very different type of graph that we would call a step graph. So we will take time to go through these. Skills on page 5. Again, you've seen that graphs do come up. So all these graph skills are important. But again, the note from the examiner that graphs and equations, there's a severe lack of skills evident. So let's make sure we build up these skills. So just looking quickly at graphs on page 6. With the Doppler effect, your graph is a rate graph. In other words, it's a graph that's graphed against time. And quite often, as you see here, the sine graph comes up. And it comes up with sound or alternating current or electromagnetic waves. And obviously, in this case, it's sound, where the amplitude of the sound varies up and down like a sine graph, like in the November 2019 paper. November 2020 had this special step graph for the Doppler effect. And in fact, we've seen it in other subject areas. We've seen it in a momentum graph, an internal resistance graph, and now in the Doppler graph. This isn't really a rate graph. Although we've got time on the x-axis, it's not a continuous change. It's a change that happens suddenly at a time t1. And perhaps it's worth just thinking about in each of these questions, what was it that happened at time t1 to cause this sudden change in momentum, potential difference, and frequency. But with momentum, it's a collision. With internal resistance, the switch is closed. And with Doppler effect, it's when the source passes the listener, and that causes the frequency to get less. So we'll look at these step graphs as well and how to answer them. So let's talk a bit about sound waves as a prelude to learning about the Doppler effect. And let's recap some of the things that you learned in previous grades. So when you talk about music, let's start at the very beginning, which seems like a very good place to start. And I showed you the notes on the piano. And as the notes go higher, these are usually what we refer to them in music, do, re, mi, fa, sol, la, ti, do. But in science, we're more concerned with the frequencies. I mentioned to you that the note called middle C in the middle of the piano vibrates at 262 vibrations a second, or 262 hertz. If we go up an octave, if we count 7 notes from there, 8 notes in all, and we come to the note C again, it's exactly doubled to 524 hertz. So the whole piano keyboard goes from about 40 hertz for the lowest note to about 4,000 hertz to the highest note. So it increases 100 times. Now the human ear can hear from about 20 vibrations a second to about 20,000. Although as you get older, you lose your ability to hear the very high frequencies. Animals like bats and dolphins and dogs can hear ultrasound at much higher frequencies. And animals like elephants can hear infrasound at much lower frequencies. Now, the way sound waves travel is a bit like ripples on a pond. As a droplet of water falls, the ripples spread out in concentric circles, and the sound from a loudspeaker is similar. As the cone of the loudspeaker vibrates, it compresses the air, and that compression wave spreads out almost like ripples on a pond. So there's 2 types of waves we identify, transverse and longitudinal. The word trans just means across. So in this case, the vibration is across the direction of movement. Electromagnetic waves like light, radio, and X-rays travel as transverse waves. Sound, which is a pressure wave, travels as a longitudinal wave. So long just means along. So the vibration is along the direction rather than across the direction. And instead of having crests and troughs, we have compressions and expansions, sometimes called rarefactions. Now it's quite useful to look at an animation which helps us compare these waves. In a transverse wave, you can see that the vibration is up and down, and it's perpendicular to the direction of travel, which you can see is left to right. In a longitudinal wave, the vibration is left and right, and it's parallel to the direction of travel. Now, sometimes it's a little bit difficult to see that these dots are only moving up and down in the transverse wave. So let me help you to focus your eye on just one dot. Look at the dot in the red oval, and you can see that it and every other dot is only going up and down, but the wave appears to be moving from left to right. That's a transverse wave. Looking at the longitudinal wave, if we focus on one dot here in the red circle, again, you can see it is only going forwards and backwards, and yet the wave appears to travel from left to right. Now, although sound travels as a longitudinal wave, it's useful for us to represent it as a transverse wave. Please remember, a graph is not a photograph. So this is not a picture of how the wave would look or travel through the air. It's a representation of the wave with the amplitude, the pressure of the air against time. Now, the height of the wave we associate with volume, with loudness, and the width of the wave, the frequency, it's also in a sense the wavelength we associate with pitch, whether something is high or low. So for example, a loud sound will be a very tall wave. You should know by looking at the ocean that the bigger a wave is, the more energy it carries. That's why tsunami waves are so dangerous. But a soft sound has got a very low wave with a very small amplitude. So the height of the wave gives us an idea of the energy of the wave, and in sound, we're talking about the loudness. When we look at the width of the wave, we're talking about pitch or frequency. So a wave that's all squashed up like this blue one represents a high note like a lady might sing, and a wave that's all spread out like this yellow one represents a low note like a man might sing. So the width of the wave has to do with pitch or frequency. Finally, we just note that when you listen to music, the sound wave for music is a smooth sine wave, and it's a wave which is repeatable and is recognizable, whereas noise, the wave is all messed up and you can't see a clear pattern. Now, this is all theory and it's all very well. And of course, probably none of you has ever seen a sound wave. But I'm going to help you to see a sound wave with the help of some fantastic software from Pasco Scientific. This is called Data Studio. So this software is getting input from my computer's microphone. And if I switch on the microphone, at the top you can see sound waves, which are showing you the sound pattern of my voice. At the bottom, we have a frequency spectrum, and it shows you which particular frequencies are dominant. Because I have quite a deep voice, you'll see it's mostly frequencies on the left-hand side. Now, if I keep quiet, then the sound wave is very flat. And if I speak quietly, you can see there's not much height to it. But if I speak loudly, you can see the wave gets very tall. So we immediately recognize the fact that we learned that the amplitude or the height of the wave has to do with whether the sound is loud or whether it is soft. Let's consider the width of the wave. Now, width has to do with frequency or pitch. Don't confuse it with volume. Volume is loud or soft, and pitch is high or low. To make this easier, let's use a musical instrument. I've got a recorder here, and if I leave the holes uncovered, the recorder will play quite a high note like this. Now you can see with the high note, the wavelengths are short, the waves are quite squashed up together, and that shows us that we've got a high pitch note. Let's see what a low note looks like. It was difficult for me to freeze that, but I think you could see that the width of the low note was much less than of the high note. So the high note again, and what happens is as that wavelength gets longer and the frequency gets less, we go from a high note to a low note. Now what about the shape of that? And let's have another look at the shape of the note. So we can see something very interesting. This is the shape of the note from a recorder. Now it's not perfectly smooth, but it is repetitive, and we can see the same shape being repeated again and again. Now you and your parents might argue about what constitutes music and what is noise, but in science, when we have a repeatable, recognizable wave shape, we call that music. Now what does noise look like? So to make some noise, I've just got a grater from the food cupboard and a spoon, and let's look at what noise looks like. Now I think what you could see there is there was no recognizable wave pattern at the top, and at the bottom every single frequency was there. So with noise we can't see a particular pattern or shape. In fact, the musical instrument that has the smoothest shape is probably just a human whistling. So look at the shape of the musical notes when I whistle. And if I freeze that, you can see an almost perfect sine wave here. And at the bottom, just one frequency selected. With the recorder, it was more bumpy because there were overtones and additional harmonics, which made the sound more interesting. So up to now, the computer was analyzing a sound which I was creating. But we can also learn these things by getting the computer to create a sound by going to Sound Creator here. Now when I switch on the speaker, you'll hear the computer play a sound. And then we can alter that sound by changing the height of the wave and the width of the wave. Let's start with the height. Now you should know by now, but the height or the amplitude of the wave has to do with the volume of the sound. Let's see how that looks. And what you saw there is that a tall wave with large amplitude is a loud sound, and a flat wave with no amplitude, there's no sound. The next thing we can do is to change the wavelength or the frequency by dragging the wave to the right. Now again, we know by now that has to do with pitch, so let's see how that affects the sound. So that sound actually became quite painfully high at the end. In fact, I couldn't even hear it anymore, because as you get older, you lose your ability to hear very high notes. So what happens with the Doppler effect is as an object passes you, it goes from high pitch to low pitch like this. So in summary, for what we've seen from Data Studio, music has a smooth, recognizable wave shape. Noise does not. So you can represent this mathematically by an equation like y equals sine x. A loud sound is a tall wave, and a soft sound is a low wave. Now again, in terms of our equation, this would be something like y equals 2 sine x with a greater amplitude. This would be something like y equals half sine x with a smaller amplitude. Amplitude is related to volume, which is measured in decibels. If you look at the width of the wave, which is the pitch, when it's all squashed up, we get a high note, which would be like y equals sine 3x, not 3 sine x, but this now goes as the coefficient of x. And a low sound would be like y equals sine x, the yellow wave here. Now you might be asking me, why do we need to learn all this grade 10 stuff again? Well, I want to tell you that in last year's exam, question 6, these were the graphs which were put together. The first graph looked like the top one with waves squashed up to 25, and the second one looked like the second graph here with the waves more spread out. That was recorded by the detector with an object coming towards it, and this was recorded by a detector in the car. Now from this, you had to work out the frequency of the sound. One of the things pupils got wrong is they imagined that they must measure the time from beginning to the end. But remember, one wave is from there, a crest, a trough, and back to the same point. So in fact, the period of this wave is not 25.5, but 17. Period of this wave is not 27, but 18. So we will spend some more time on that when we look at that question. But this understanding is very important. Just to remind you of some of the naming of transverse waves, crests are the high points, troughs are the low points. If we measure AB or BC, each of those is one wavelength. And a wavelength is between points which are in phase, like, for example, between two troughs or between two crests. The frequency is the number of wavelengths that pass in 1 second. The amplitude is the height of the wave, but not from top to bottom, not from crest to trough, but from crest or trough to the mean position there. Speed of the wave is the distance the wave moves in 1 second. We know that, for example, sound waves travel about 300 meters in 1 second. Light waves travel 300 million meters in 1 second. Very different. That's why we see lightning before we hear the thunder, even though they're produced at the same time. The period is the time taken for one wave to pass. So period is just the reciprocal or the inverse of frequency and vice versa. Now the wave equation is also very important, and we need to know how to find out wave speed. So remembering a wavelength is from A to B or from that point to that point. The speed of a wave, speed is always distance traveled over time taken. So let's make that the distance per wave divided by the time taken for one wave. Now the distance per wave is just the wavelength, and the time taken for one wave is the period defined on the previous screen. And therefore we have this wave equation that wave speed is wavelength over period or wavelength times frequency. So you can put it in this triangle so it's easy to manipulate. Speed of the wave equals frequency times wavelength. So frequency is speed over wavelength, and wavelength is speed over frequency. Now again, some comments from the examiners from the November 2019 exam. They said a number of candidates could not interpret the graphs in terms of wavelength, period, and frequency correctly. And also their comment was that we need to revise the use of the wave equation, V equals F lambda, and the period equation because pupils did not know it. So let's take a look at what the Doppler effect really means in real life before we go to the maths and to the equations. Now, I'm actually sure that everybody has had first-hand experience of the Doppler effect with sound, because it's what happens when you're standing by the side of the road, the car's driving past you quite fast, and you hear something which sounds like this. And you hear that characteristic change from a high-pitched sound as the car approaches you to a low-pitched sound as the car goes away from you. If you drew a graph of frequency against time, you'd see a constant high pitch and then a sudden drop as it passes you and a constant low pitch. Remember the November 2020 question had such a graph. Now the reason for it is clear. As the ambulance with the siren approaches the person, the waves in front of it get squashed up. The frequency is higher, and so we get a higher pitch. As the ambulance goes away from the person, the waves get stretched out, their frequency gets lower, so we have a lower pitch. Now, I'm going to show you two simple videos that we took just with a cell phone camera of a car driving past a stationary observer blowing its hooter. In the first video, you'll be able to hear the characteristic change in pitch. In the second video, the video is actually filmed from inside the car. And because there's no relative motion, because the listener is traveling with the source, there'll be no change in the pitch of the hooter. So I hope you were able to hear that change in pitch in the first video, which we played twice, and notice that when the recording was done inside the car, there was no change in pitch. Now, apart from listening to cars going past, the Doppler effect is very helpful, and it can be used to measure the blood flow in the heart without having to cut the person open or do anything inside the body. An ultrasound probe like this one can determine the direction of flow and relative velocity of the blood by calculating the frequency shift caused by the flow of a sample of blood. So great use of this effect in technology. Now, the Doppler effect, which we hear for sound, is a change from high pitch to low pitch. But because it's a wave effect, it affects all waves, including light waves. And what we get with light waves is a blue shift and a red shift. Now, of course, we need a telescope or some sort of optical instrument to detect light. If we look at light from distant stars which are approaching the Earth, the light would seem to be blue shifted. And again, the waves are getting squashed up and their frequency becomes higher. If we look at stars which are moving away from the Earth, we would see a red shift as the light gets stretched out and the frequency becomes lower. So this is what it looks like in practice. We use a prism or diffraction grating to look at a spectrum. If we're looking at something like the sun, which is a fixed distance from the Earth, we get a normal spectrum from purple through to red. If we're looking at a distant galaxy which was moving away from us, the spectrum would be red shifted and we'd see a shift towards the red side. If it was approaching us, we'd see it blue shifted. So here's another way of looking at it. This is what the spectrum would look like from the sun, a normal rainbow. But when we look at distant stars, we actually see something which looks like the bottom picture. Now that tells us it's red shifted, and that tells us they are moving apart from us. In fact, every time we look at the light from distant stars, we find it to be red shifted, and that tells us that all of these stars and galaxies are moving apart from us. That's a good thing, because if they were moving closer, we could be on a collision course. Now, this helps us to decide that a good model for the origin of the universe was the Big Bang model, that there was an initial explosion, and that since then the universe has been expanding, almost like an inflating balloon. So everything in the universe is moving further apart from the Earth and further apart from each other. And the evidence from that comes from observing redshifted light from distant stars and galaxies. So let's investigate this Doppler effect for a moving source. So here you have an ambulance with the siren going, and because the ambulance is moving, we have this Doppler effect, that the waves in front of the ambulance tend to get squashed up and you get a higher frequency, 820, but as soon as the ambulance is passed, the waves behind the ambulance are stretched out and you get a lower frequency. So just observe as it passes. The siren has a frequency of 800 hertz, but in front you hear 820, and behind you hear 780. And that is the Doppler effect. Now, of course, if the source is stationary, if the ambulance is not moving and the observer is not moving, then it doesn't matter where you stand, you will always hear an 800 hertz sound. So the Doppler effect works with relative motion. It doesn't really matter whether the source or the listener are moving, as long as they're moving relative to each other. So in this case, there would be no Doppler effect. Let's investigate that a little bit more by looking at a great web animation. So this animation allows us to change the speed of the wave source. You can see at the moment I've put the speed as 0. The wave frequency is going to be 3 hertz, 3 waves per second. And then what I can do is simply start the animation. And you can see as the waves move outward, 3 waves per second, because the source is not moving, it doesn't matter where you stand, you'll experience 3 waves per second. So there's no Doppler effect because we have a stationary source. Let's pause that. And then let's give the source some speed. In this case, it's going to be 0.5, half the speed of waves in that medium. Now, have a look at what happens now when I replay. You'll see the shape is really quite different. And you'll see if I pause it here, the wave fronts in front of the source are squashed up. There's a higher frequency. The wave fronts behind the source are stretched out. In terms of sound, you'd hear a high pitch and a low pitch. In terms of light, you would see a blue shift as it approaches or a red shift as it leaves. And if you just look, you can see that the waves hit this wall very often, but they don't hit this wall quite as often. And that is a Doppler effect. Now, just for interest, let's actually give the source the same speed as the speed of waves in that medium. And let's see what happens when an aircraft, for example, flies at the speed of sound, because it's very interesting. So here's the source, and because it's flying at the same speed as the waves can't escape in a forward direction. So if this was an aircraft, you wouldn't hear it until it was past you. And you can see this huge buildup of pressure, and we get something called a sonic boom. A loud bang is heard as that aircraft passes overhead. So this is flying at the speed of sound, which is called Mach 1. What would happen if we flew faster than the speed of sound? Let me set it as 1.5 times the speed of sound, and let's restart that. Now that the source is flying faster than the speed of sound, you can see it leaves the sound waves behind. And we get something that's called a shock cone over here. And again, if this aircraft flew over you, you would only hear it when it had already passed by. So to recap what we saw from the web animation, if the source is stationary, we get no Doppler effect, and it doesn't matter whether you're in front of the source or behind, you would hear the same frequency because there's no relative movement. If the source was moving, you can see clearly that in front of the source as it approaches, you hear a higher frequency. Behind the source as it leaves you, you would hear a lower frequency. If you travel at the speed of sound, we get this effect where the sound waves can't go in front of the aircraft. Now, the speed of sound was broken on October the 14th, 1947 by this brave man, Chuck Yeager. He flew a Bell X-1 experimental aircraft and was the first man in history to break the speed of sound 73 years ago. If you fly faster than the speed of sound, you get this shock wave. Now, you can see here as an overhead picture of a boat. The speed of the boat is faster than the speed of waves on water, which of course is very slow. So you can see this shock cone behind it. But an even more spectacular picture here, you can see a fighter jet. It's just broken the sound barrier, and the intense buildup in pressure actually causes a cloud to form. And by looking at the angle of the shock cone, we can actually determine the speed of the jet. Here's another spectacular picture, two jets, and this one just as it breaks the speed of sound and causes a sonic boom. So it's great to get a conceptual understanding of the Doppler effect and what happens and how the pitch changes, but it's also very important to be able to describe it mathematically. Using this equation, the Doppler effect equation, which you'll find on page 38 in your booklets, which is the first page of the data sheets. This equation usually causes a lot of trouble for students because of all the different pluses and minuses. So let's sort this out. So take a look on page 55 of your books, and let's start with the variables which we come across in the Doppler effect, because it's important to understand these. We start with the variables from the wave equation, V equals F lambda. There's four simple variables you should know by now. V is velocity in meters per second. Lambda, the Greek letter, is wavelength in meters. F is frequency in hertz. And a hertz is just the inverse of a second. So 1 hertz is 1 over a second, or s to the minus 1. Then finally, T is a measure of time, but specifically the time for one complete wave or vibration measured in seconds. And T is the inverse of F, so T equals 1 over F. Now for the Doppler effect, we use the subscripts L and S to refer to listener and source. The source is producing the sound. The listener is observing or hearing the sound. So F subscript L is the frequency observed or heard by the listener, whereas Fs is the frequency produced by the source. VL is the velocity of the listener, Vs the velocity of the source. Now, in metric, one of these two will usually be 0. You don't normally have problems where both the listener and the source are moving. And finally, just V by itself is the velocity of sound. Usually that's given to you in the question, and usually that's 340 meters per second for the velocity of sound in air. So all of these are at the top of page 55 in your book. So you can see as we apply them to the diagram here, we've got two listeners actually on either side. They're both stationary. So VL in this case would be 0. VS is the velocity of the source, which is an ambulance. FS, the frequency of the source, is 800 hertz. That's the actual real frequency of the sound being produced by the ambulance. And the same frequency would be heard by the ambulance driver. But because of relative motion towards this listener on the right, he observes a higher frequency. Because of relative motion away from the listener on the left, he observes a lower frequency. You can also see how the waves seem to be getting squashed up in front of the ambulance and stretched out behind. So we expect that where the source is moving towards the listener, the frequency observed by the listener will be greater than the frequency of the source. Where they're moving away from each other, the frequency observed by the listener will be less than the frequency of the source. Now, in fact, you can simplify this complicated equation just by taking note of the fact that it's only relative motion that is important. And at the bottom of page 55, we've summarized this into a table. So taking the Doppler effect equation, remember it's on page 38 in your booklets. It's at the bottom of that page of the data sheets. We can simplify it into 4 different forms. Now, please don't try to learn these 4. You don't need to learn them. If you understand it, you can simply adapt the main equation. And the only important thing is, are the source and the listener moving towards each other, or are they moving away from each other? Now, let's look at each of these in turn, because it'll make more sense if we do them one at a time. So the first example, a source moving towards a stationary listener. So here's our listener. It's a police car. It's stationary, so the velocity of the listener is 0. The VL is 0, and that's why at the top we've just got V, because VL disappears because it's 0. Now, our source, the car with the alarm sounding, is moving towards the listener. Remember, that means that the source has a particular velocity, Vs, which we're going to find at the bottom of our equation. And quite often the question will ask you to calculate that. Now, we expect here that the frequency observed by the listener in the police car will be greater than the frequency of the source because they are moving towards each other. Now, if you want a fraction to be greater than 1, then you need a plus sign on the top and a minus sign on the bottom. So we simply use the form which has the plus on the top, which we don't see because VL is 0, and the minus sign at the bottom. So all you need to remember is to substitute in VL equals 0, and that it is plus over minus. And you will very simply come to that. Let's look at the second example. In this case, the listener is moving towards a stationary source. So the source, the car with the alarm making a noise, is stationary, it's parked. The Vs equals 0, and it disappears from the bottom of the equation. In this case, the listener, the police car, is moving towards, but once again, because of that, the police car will now have its own velocity, so VL is non-zero, and often you'll be asked to calculate that. But now we expect again that the frequency observed by the listener will be greater than the frequency of the source because they are moving towards each other. For greater than, we need plus over minus. So we simply choose the version with the plus sign at the top and the minus sign at the bottom, which we don't see because Vs equals 0, and that term has disappeared. The third example is where the source and listener are moving apart. So again, the listener, the police car, is stationary. The source, the car making the noise, is moving away. So it has its own velocity, whereas VL equals 0, and VL disappears from the top of the equation. But now we expect that the frequency observed by the listener in the police car will be less than the frequency of the source because the waves are being stretched and they arrive less frequently. If we want FL to be less than FS, then that fraction needs to be less than 1. So then we need the form with minus over plus. And so at the bottom where you have 2 terms, you will choose the plus sign in order to make that fraction less than 1. And finally, one more example of source and listener moving away from each other. In this last case, the last line on the table at the bottom of page 55, the source, the car with the alarm making the noise, is stationary. So Vs equals naught, and you don't see it at the bottom of the equation. The listener, the police car, is moving. So its velocity is not naught. It appears at the top of the equation, velocity of the listener, and you'll probably be asked to calculate that. Because they're moving apart, we expect the frequency observed by the listener to be less than the frequency of the source. So that fraction needs to be less than 1. So therefore, we choose the form with minus over plus. So it's a minus sign on the top. The bottom has only one term. So if you pay attention to this table at the bottom of page 55, it will help you to choose the correct form of the equation just by understanding the situation, because all that matters is where the listener and source are moving towards each other or away from each other. This will also become clearer if we look at some illustrative exam examples. Now, this is not in your booklet, so just pay attention on the screen. Here's a typical exam question from a previous exam. A car is traveling towards you at 30 meters per second, sounding its hooter with a frequency of 300 hertz. Velocity of sound is 340 meters per second. What is the frequency of the sound that you will hear? Now, choosing the equation is simple because you know it has to be the Doppler equation from the bottom of page 38. But which form of the equation are we going to choose from our table? Well, in this case, the car, which is the source, is moving, and you as the listener are stationary. So it's definitely going to be the first line, and we're going to use this form of the equation. So source is moving towards a stationary listener. You're the listener, you're listening, and here the source, a car sounding its hooter, is moving towards you. So VL equals naught, and that disappears from the top of the fraction. The velocity of the source, we know it's 30 meters per second. You're told this. And we also know that the frequency of the source is 300 hertz. We were told that. We expect the frequency observed by the listener to be greater than that because they are moving towards each other and the waves are being squashed up. So we choose that form of the equation because it's plus over minus to make frequency of the listener greater than the frequency of the source. Then it's simply a matter of substituting in. V is the velocity of sound, which we substitute top and bottom, 340. 30 is the velocity of the source, which we get from the question. And 300 is the frequency of the source we've identified here. That really is a very simple substitution. And then all that is left is to solve. And we get an answer of 329 hertz. Let's check, is it greater than the frequency of the source? Yes, it is. If we'd got 270, we would expect that we had made a mistake somewhere. One more example. Again, it's not in your booklet. Just look at the screen. I'm not actually going to solve this completely, but just help you to choose the right form of the equation, because from there, it's just a matter of substituting and solving. The siren of a stationary ambulance emits sound waves of 850 hertz. So this ambulance is the source, it emits sound waves, and it's stationary. The listener, the car traveling towards the ambulance, measures a frequency of 900 hertz. What is the speed of the car? So stationary source, it must be the second or the fourth column, and the listener is moving towards, so it's definitely that one there. And this is very simple to calculate. You want to find out the velocity of the listener. We know the speed of sound will be given to you in the question as 340. Frequency that the listener hears is 900. Frequency of the source is 850. You substitute in and then you solve. But let's move on to some actual exam questions from recent exam papers. So let's take a look at exam questions which have been asked recently about the Doppler effect. On page 56 and 57, you'll find 3 questions. They total 31 marks. So as always, if you can pause or stop the video here for 31 minutes while you try to complete these. Again, I cannot stress enough how important it is for you to try these for yourself. Right. Let's have a look at the correct answers and compare with your answers. 6.1 is a recall question we're not going to do now. 6.2 is the patrol car driving towards or away. Well, you're told the drive of the patrol car has a frequency which is lower. Lower frequency means that you are driving away from. So we'll just deal with those quickly. And then moving on to the main questions, calculate the frequency of sound emitted by the alarm and calculate X, the distance the patrol car moves in 10 seconds. Now, let's have a look at the situation. So we've got a stationary car, which is the source. Its alarm is going off. So VS, the velocity of the source, is 0. How do we know what the frequency of the source is? Well, it's 1,000 hertz. That's 6.3. You just simply do the calculation. Frequency equals C over lambda. Speed of sound, 340 divided by lambda 0.34 gives you your answer of 1,000 hertz. That will give you 3 marks. Now, it's emitting sound of that frequency. We have a police car which is traveling away from it. We don't know the velocity of the police car. That's actually what we want to calculate. But it observes a frequency 50 hertz lower. So the frequency of the listener is 950 hertz. Please don't think it's 50 hertz. And of course, the speed of sound in air is given 340 meters per second. That's one of the obvious things. Now, going through our progress method, which we learned in section 6, draw a picture. Well, you've seen the picture. What is required? And this is an important one because the question asks for X, the distance the patrol car moves in 10 seconds. Actually, what it's asking for is VL, the velocity of the listener. And you'll calculate that very quickly. From that, you can very quickly calculate what X is. What is obvious is that the patrol car is moving away from the source. We know that because it hears a lower sound, and the velocity of the source is 0. What are you given? Well, you're told the frequency of the source is 1,000 hertz. You calculated that. Frequency of the listener is 950, and the speed of sound. So we need to relate the velocity of the listener of the patrol car in terms of those other 3. So we go to our data sheets on page 38, and as always, there's just the one Doppler equation, but we need to put it into the correct form for this question. Now, you've got a stationary source, you've got a moving listener. So the source is stationary, so it must be the second or fourth row. The listener is moving away from, so in fact, it's the fourth row, and we're going to use this form of the Doppler equation. There's no need to learn all of these. Just remember, because the frequency of the listener is going to be less, you have the minus over plus form of that equation. So let's complete the progress method. We have related things together by finding a correct form of the equation here. And we know that's correct because the frequency observed by the listener is lower than the frequency of the source. Substitute in 950, the frequency of the listener, 1,000, the frequency of the source, speed of sound, and we solve that carefully for VL, the velocity of the listener, and we'll get an answer of 17 meters per second. Now, the question actually said, what is the distance traveled in 10 seconds? And that's just simply multiplying velocity by time, and we get 170 meters as our answer. Please make sure that your final answer is that distance and not actually that velocity over there. Now, just for this first exam example, let's have a look at how it's marked. It's worth 6 marks. The first mark was for correctly taking the Doppler equation from your equation sheets. The second mark for using the correct form of the equation. The third mark for calculating the frequency of the listener at 950 and then substituting in the other figures correctly. The fifth mark for getting the velocity of the listener at 17 meters per second, and the final mark for calculating X, the distance traveled in 10 seconds, as 170 meters. So let's have a look at November 2019. Now, the 3 Doppler questions we have together here are all very different and are actually quite difficult. And this is the one that caused all the trouble with learners because they weren't used to seeing these sound wave graphs. So I really want you to look back in this video because we did deal with all of this. So question 6.1, which phenomenon is illustrated? It's the Doppler effect. Then they tell you the police car is moving away from detector Q. How do you know? Well, simply because Q records a longer period, 27 compared to 25.5, and therefore a lower frequency. Now, I want you to remember earlier in this video, we talked about high pitch and low pitch. We said a high pitch graph is all squashed up and a low pitch is all stretched out. Now compare it with the two graphs you've got here. There is detector P, which is more squashed up, and there's detector Q, which is more stretched out. Another thing that's very important is to remember that the period of a sound wave is that. Or you can measure it between two crests or between two troughs. But the period is not from the beginning to 25.5. That is actually 1.5 periods. So let's start with the beginning question. 6.3, calculate the frequency of the sound waves recorded by detector P. Detector P is in the car, so it records the actual frequency of the source. So as I said, the period is up to 17 seconds, not 25.5. So it's a simple calculation. The period is 17 times 10 to the minus 4 seconds. Don't forget that. The frequency is 1 over period, which is 1 over that figure, which is 588.24 hertz. Now, although it's not asked for immediately, let's do it for the detector Q, the stationary detector next to the road. The period was 18 times 10 to the minus 4 seconds. So calculating the frequency, we get a lower figure, 555.56 hertz, which we note is less than the frequency of the source, as we expect, because the police car is moving away from the source. Now, looking at our progress method, we have a stationary detector by the side of the road. We have a police car moving away, making the sound. We don't know what the velocity of the source is, but we know that the frequency observed by the listener will be less than the frequency of the source because the waves are being stretched out as that police car moves away. And we know from our previous calculations, frequency observed by the listener was 555.56 hertz, and the frequency produced by the source, 588.24 hertz. So there's our picture. What is required is Vs, the velocity of the source or the police car. What is obvious is the source is moving away from the listener and that the velocity of the listener, the detector, is stationary. What are you given? Well, we've calculated these frequencies so far from 6.3 and from the graph, and we're given the speed of sound in air. So we need to find the velocity of the source in terms of these three quantities. But first, with the equation, we need to choose the correct form of the Doppler equation. By now, we know where to find that Doppler equation on our data sheets. So let's have a look. Again, there are 4 forms here. We had a stationary listener in this one, so it must be 1 or 3, and the source is moving away, so it's definitely the third one. So we're going to use this form of the Doppler equation. Okay, so again, just to animate it to make it clear, a stationary listener, the source is moving away. And so we don't know the velocity of the source, so we're going to be using this form because the frequency of the listener must be less than the frequency of the source. So it's in the form of minus over plus. These are the frequencies which we calculated in the first part of the question. So we simply take our Doppler equation, we substitute in frequency of the listener, 555.56, frequency of the source, 588.24, speed of sound, do the calculation carefully, solve for Vs, and you'll get an answer of Vs is equal to 20 meters per second. So here the final calculation was not difficult, but finding these frequencies from the graphs is what caused a lot of difficulty. So make sure that you understand that and rewind and play it again if you don't. And finally, the November 2020 question 6, which you'll find on page 56 in your books. Again, a graph, but a completely different graph. It's a frequency time graph, but it's not a rate graph. It's a step graph because the frequency is 3148, and suddenly at time t1, it drops to 2073. As usual, we won't worry about the recall question, but you need to worry about those because it's 2 marks for you. 6.2 says, does the detector record the frequency when the train moves towards it or away from it? Well, we notice the frequency is dropping. So dropped from 3148 to 2073. So it must be towards, because it's observing that higher frequency. The main part is calculate the speed of the train. And the speed of sound in air is 340 meters per second. Now, the problem is, although we know the two frequencies observed by the listener, we don't actually know the frequency of the source. So this is quite a tricky one, which will involve simultaneous equations. Let's have a look at it. So first of all, let's decide what form of the Doppler equation we're going to use. There's the general equation from your data sheets. Now, we've definitely got a stationary listener in both cases, but the train is first of all moving towards. So that's the equation we're going to use for before, and afterwards the train is moving away. So that's the equation we're going to use for after. So we'll actually have to write two equations for the two different situations. So a stationary detector, the train is moving towards it before. We don't know the speed of the train. And afterwards, again, we've got a stationary detector. Train is moving away. Again, it's the same speed of the train, which we don't know. But these are the two frequencies which we got from the graph. Higher frequency before and a lower frequency after. So using our progress method, a simple picture has been drawn, and it is helpful. What is required is the speed of the train, Vs. Remember, that's the same before and after. What's obvious is the direction of the train towards and away, and that the velocity of the listener, the detector, is 0. So we're given the two frequencies from the graph, and we know the speed of sound. So we need to find the velocity of the source, the train, in terms of these. The problem is that we don't know the source frequency, but we do know when we use this equation that VL will be 0. And for position 1, the bottom is going to say V minus Vs. And for position 2, it will be V plus Vs. Let's look at the situation. It will be much easier to do it before and after separately. There's the general equation. When we look at before, because the train's approaching the listener, we have this form of the equation here. And we can substitute in the frequency observed as it approached was 3148. Speed of sound, we still don't know the frequency of the source. For scenario 2, after the train has passed, we have the equation in this form. Because the frequency is less, we have the plus at the bottom. Again, we fill in our values, 2073 from the graph. Speed of sound, again, we don't know the frequency of the source. So the problem is we have two unknowns, Vs and Fs, and we need both of these equations to solve. So what we will do is we will simply divide equation 1 by equation 2, and the Fs's will cancel. And also the 340 on the top will cancel. Do it for yourself carefully, but we will get something that looks like that. Now we only have one unknown, velocity of the source, and we can do the calculation carefully, and that will give you a final answer that the velocity of the source is 70 meters per second. This is quite tricky, so take time to make sure that you understand it. So we've calculated the speed of the train in 6.3 was 70 meters per second. A final question for 2 marks. The detector started recording the frequency when the train was 350 meters away. Calculate the time t1. So they're really asking you, how long would it take this train to cover a distance of 350 meters at a speed of 70 meters per second? This is just a simple equation of motion. Delta t is delta x over v from the definition of velocity. Fill in the values. Delta x is 350, that was given. Velocity is 70, we calculated in 6.3. And the simple calculation gives you an answer of 5 seconds. So that's all on equations on the Doppler effect for now. Just remember, your education is really important. Nelson Mandela said it's the most powerful weapon that we can use to change the world. Thank you for watching.